So in the second part of our perturbation theory lecture, we're going to have a closer look at specific orders to be able to assess their meaning, how they are derived, and what knowledge we can gain from this. So sorry about the catch, it's a bit temperamental. What I'm gonna do now is I'm going to have a look at these expressions order by order, and we're going to commence with the most widely used order, which is the first order term. So in principle, we could go to as far as we would like to. Bear in mind that for this series to converge, your perturbation has to be small. But we're going to focus here on the simplest cases and consider the first order term. So let us assume, for simplicity, that the system is initially put I at an eigenstate phi j of H naught. So we can make this assumption. And remember that at t equals 0, Schrodinger picture and interaction picture coincide, although I'm putting I here to point out we are working on the interaction picture. Note as well that Cm dot 0 is equal to 0, so that Cm dot, the first order, can be a constant, or it has to be a constant. So we have some flexibility there. So here this means that Cm0 is a constant. If initially we are in phi j, which is an assumption that we are making here without loss of generality, then we can say that Cm0 is delta mj, because then if you are in a state that is not phi j, your amplitude to a zeroth order is going to be 0. It has to be 0. Now, this assumption here is something we're making to derive this, but it allows you some flexibility. For instance, you could consider that your system is initially in a coherent superposition, or depending on the problem that you are going to take care of. But we are going to stick with that for now. And just to emphasize, this is an eigenstate of H naught, and the eigenenergy eigenenergy EJ. Let's write in the first order term. So we have a look at this expression which we had. And if you remember correctly, we had this ck naught, which we got from the right-hand side of the equation, and Cm dot 1 was given by this. So if we consider we're initially in a single state, which is our phi j, this implies that our first order term, which is Cm dot, is given by this, is 1 over IH bar exponential I omega mj. Now, you had a whole sum, and the only term which is going to survive from that whole sum over k is the term in which k is equal to m. So that's why I'm writing this already. So you have Vmj t. If you would assume, for instance, that your system is a coherent superposition, we would have two terms surviving, etc., etc., etc. But we are assuming starting from an eigenstate. And we also need to limit the time for which we are switching on or off our perturbation. So this is also another assumption that we'll make. And we keep this time for the moment finite. So our perturbation is switched on for 0 t tau, so a time between 0 and tau. And we can then make equality, so take it really from 0 to tau. And we can integrate this. So if you look at this expression, we have two possibilities. We could have the possibility that m is equal to j, or m is different from j. You don't know. So we have these conditions. Let's compute things. So let's assume then that m is equal to j, which means that the system remains in that state. So in this case, you have Cj1 t 1 over IH bar integral from 0 to tau dt Vj jt, whereby remember that this is going to be phi j Vt phi j. We need to discuss if this is going to be non-vanishing or vanishing. This is going to depend on what your V is. Some cases it will, sometimes it won't, but let's bear this in mind. And if m is different from j, we find that Cm to first order of tau is 1 over I h bar 0 to tau dt v mjt ei omega mjt, whereby once more this is phi m vt phi j. Now this means that in this case you are having a transition from one bound state to another. And so let me write here, system remains in the same eigenstate, and here the system undergoes a transition from phi j to phi m, whereby m is different from j. So for instance, this couldn't happen if you had here an operator that is odd, and you had two states with the same parity, which is for what you have a lot when you have light-matter interaction. We're going to see that as well, but it would be perfectly fine here. And if you undergo a transition, meaning in this latter case here, you can also define transition probabilities going from J to M or the other way around. In this case, J to M, because you assume they started at J. So your transition probability will be P to first order from J to M, tau, Cm to the power 1, tau square, like the modulus square of the transition amplitude, because this is a transition amplitude to first order perturbation theory, that the system goes from J to M. So the corresponding transition probability is the modulus square of that. And we can say also that if Cm1 tau is different from 0 for M different from J, then there is a non-vanishing probability that the system will be found in phi m. I mean, this is not surprising because many times what is happening is that you have a coupling due to an external field or some kind of many-body correlation, and you couple different states. And this means that you're going to have transitions that are going to occur. This is absolutely normal and is absolutely fine. It's something to a certain extent that you even expect. So this is absolutely okay. And how about the system being in the initial state? I mean, there may be a finite probability as well, right? So let's go and talk about the probability of the system remaining in phi j. Okay, in this case, you have to consider the zeroth order probability. To zeroth order, you had something like 1 plus cj to the power 1, which is the that coefficient when they were equal to square. Now remember that you can say, but this is bigger than 1. No, this could be negative. You don't know. Or you could even have 1 minus the probability that it got excited to. So if the perturbation is weak, we expect that this is going to be very close to 1. It's going to be probably smaller than 1, but it's going to be quite close to 1. And we are dealing here with a perturbation. It's not like you have some coupling with some strong fuse that is brutal and is gonna change your system and start ripping off things. Okay, it's my area of research, so that's the example I'll give you. But this does happen. I, for instance, cannot use perturbation theory, at least not in this standard form, because a key assumption is that the perturbation is not changing a lot. The physics of the system is changing a bit, but it's not changing a lot. So you are closer to your unperturbed Hamiltonian. You're like disturbing things a bit, but they're not like a major disruptor. So we expect that this is closer to 1, and the perturbation should be weak. So this will be close to 1, hopefully smaller than 1. Yeah, it has to be smaller than 1, or it never happens. But you were going to have some disturbance. It's close to 1. So what we can do is we can compare these to first order. So for simplicity, we can say that CJT or CJ tau, if you wish, is approximately, here we are neglecting, we are setting lambda equal to 1 is a bit strange, but we have some arbitrarity to do this. If your VT is weak enough, although we used it to get all these expansions done. But if you realize the expansions, they don't depend on lambda, the expressions that you get in the end equating term by term. So this is pretty much okay. And if I go to first order, I'm going to have, this is going to be to first approximation. Here, just remind us, set lambda equal 1, which I can do. You get 1 plus 0 tau dt vjjt, which you could also say, okay, if I expand this to first order, because this is expected to be small, say if you consider, for comparison, you have e to the power minus I over h bar, 0t d tau vjjt. To first order, this is going to be 1 plus, approximately, okay? 1 plus minus I over h bar, integral 0t d tau vjjt. Can you see that this correction is like a phase shift? So to first order, the correction that you introduce due to the perturbation is like a phase shift. So we can say that to first order, the correction due to the perturbation is equivalent to a phase shift so that you can write that Cj tau is approximately if I phi Cj naught, whereby phi is minus 1 over h bar, integral from 0 to tau dt vjjt. So Why am I stating that? Because this probability that the system remains initial state is close to 1. You know, because if you have something that to first order expansion is a phase shift, when you take the modulo square, that is going to cancel out, right? And you say it's just a phase. So what is going to happen to you is that this probability is going to be very close to 1. And all these transition probabilities, first order that we're talking about, are going to be quite small. It doesn't mean that transitions are not going to happen, but it means that the probability is small. So depending on the situation you're dealing with, you may need to go beyond first order or even further. So how do I go if I need to compute second order correction? Let's look at the expression that we had. So we have computed first order term. And what we can do is we can substitute this into the equation that we had for the first or for the second order that led to that recursive relation. And we can then obtain it. So we're going to assume that the perturbation is switched on at time t equals 0 from and that you are going to have phi j as your initial state. So assumptions are going to be the same. So assumptions phi equal phi j. And we know already the expression for the second order. Remember that Cm dot t was 1 over I h bar sum over k e I omega n k t v n k t c k to the first order t. But now remember that we know the first order. We have just calculated the first order term considering these conditions. So we can just plug it in, and we are going to consider this case where we have j different from m, and when we insert it, so inserting expression for C1, CK1T, we're going to have and I can integrate as well. So I'm going to have then that Cm is going to be 1 over I h bar to the power 2 sum over k integral from 0 to tau dt dash exponential I omega mkt. I'll put this dt, and here you have ckt, so you have integral from 0 to t of t dash, I need more space, you know. VMK T dash E I omega MKT dash. So what I have done was the following. I have inserted the expression that we have here for CK1T, considered M different from J, which was this guy. And on top of that, I integrated from 0 to tau here. So a few interesting things here that we have considered. Notice that we have first time ordering. That here I'm going from 0 to t, whereby t is something between 0 and tau. And here I go from 0 to tau. So I'm having some kind of nested integrals that appear a lot. If you would go, for instance, third order perturbation theory, we would have like 3 nested integrals. Note also that we have a missing one. Hang on. I had here, sorry, I forgot. VMKT. And here I have some kind of VMJT dash. Okay. Yeah, I really no VKJT dash, because this is going from J to K. Sorry, this is getting messed up. So this is from J to K. So here I have K, J, and here I have from K to M, and I sum over K. So this got a bit messed up, so maybe I should do it a bit slowly. Note that we have some sums here. First, here I don't have N, I have MK, because I am considering that I have a sum over all these K states, but I have this amplitude associated with M. Then when I plug this in, I have CK1. I don't have CM1. So CK1 would be this expression here, but instead of M, I would have K. So I have here VKJ and omega KJT, which means that here I don't have this same M, because this M here is the final state. So I have here K, I'm taking from J to K, and I end up with something that has a sum over these intermediate states K. So this is something that is quite nice. And I have dt 0 t dt dash, and then I'm just writing it in a nicer way so that we can have a look. E I omega mkt vmkt vkjt dash E I omega kjt dash. Why am I writing like this? for the following. You can see first that we have this time ordering, which I mentioned before. And also we have these matrix elements here. So these are as if you were going through some kind of intermediate states, K, from the initial state J to the final state M. So this is part of some observations that I'm going to make about this specific case. So please note, first thing that we have is we have time ordering. Which means that first we integrate from 0 to t going via t dash, and then this t is a time which goes then, this is an intermediate time before 0 and tau. So we have time order nested integrals. And if you had third order perturbation theory, you would have more and more nested. You have 3 nested, for instance. Then you have intermediate states phi k. Where do you see that? You see this from the sum over k, and you see this from this transition amplitude that goes from the initial state j to this k, and then from k to m. And these matrix elements. So, and I'm going to write that we know initial state phi j, final state phi m. If you want to think about it, for instance, a very interesting example is like when you have a 2-photon transition and you have, for instance, you have something intermediate. Can be virtual or it can be real. You have phi j and you have phi m, and you go like this. From here and then from here. So here you would have one matrix element which would be phi m v phi k. Here you would have phi k v phi j. But if you don't know what these things are, then you have, for instance, a sum over this. You could have several possible intermediate states. You don't have just one. And one thing that we also have done also for the first order was the following. We have considered that lambda was equal to 1. And why on earth can I do that? You know, I'll write for the first. So for first order, you would have, if you have a transition, you just have like final state phi m, initial state phi j. You have a transition from here to here, and you have a coupling phi m v phi j, right? So for both cases, we have for first order, especially when we discussed the probability of the state remaining the same, we have set lambda equals to 1. This is tricky. You can call me someone very sloppy because it looks very sloppy. So we have said then in principle that this is what is happening. CMT, CM0, T plus CM1, T plus, etc. So that at the end of the day, you would have CMJT. First, we equate all the terms with equal lambda. And then we say, ah, but the expressions that we got in the recursion relation, they were independent of lambda, so we can make this assumption. And then you can ask, is this going to converge? It's a bit sloppy, okay? But we use that more as a means to get the expansion, because you are going to have a V which is unbelievably small. It's very, 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 very small. So first question here, convergence. Like, Carla, you're cheating. A little bit. But what is going to happen is, this is okay if lambda is, if V t is small. So which is actually the key idea behind a perturbation. You have to have something that is small. And in practice, this is going to work extremely well depending on the system you're taking care of. And the results of first and second order, they are used widely in physics. Not in my area, again, but in many areas of physics, like for instance, quantum optics, etc. They are used widely. Now, there is a nicer way of deriving these that I have derived for you. And this per se is worth a remark, and a good one. So one can start much more elegantly doing all these computations. I mean, we have done this in a simple way, but for instance, and this is an important observation, so like important in red. We can write transition amplitudes in integral form from the start. One can write perturbative transition amplitudes, and you can mess around with more actually. Transition amplitudes in integral form from the start using time evolution operators. Using time evolution operators. I mean, why did we learn all that machinery after all? So let's say, and I'm gonna exemplify this a bit here because I think it's an important point. Let's say you consider you have H, which I'm not gonna put any lambda now, H naught plus H int t, okay? And I have then that U t t dash is associated with the whole guy. So this is time ordering exp integral of H S gs I H bar if you want. Yeah, H bar is all. Okay. The other one is, let's say, U naught T T dash is associated with H naught, which we can assume to be time dependent or time independent. So this is time evolution operator. So this is associated, let me write, full Hamiltonian. And this is U is the unperturbed time evolution operator associated with the unperturbed Hamiltonian. One thing we can do that is exact is we can write, so this is, in some places you find this as Duhamel equation, in some places you find as Dyson equation, okay? So I'm gonna put both names. So we have the Duhamel formula, or Dyson equation. And what you do is you write U t t dash is equal to U0 t t dash minus I over h bar t dash to t u naught t t double dash. Here you have h int. If you need, remember this is the interaction Hamiltonian. It's not necessarily the Hamiltonian in the interaction picture. I'm not making any assumption here. T dash, no, double dash, and then here you have u. I need more space, always. Let me cut this. Yeah, I didn't want to take it all the way. Okay, it's good. So this is exact. This is an integral equation. And if you see, you have here the full time independent the full time evolution operator associated with the full Hamiltonian H, which is this guy, whereby this is the unperturbed part and this is the perturbation. Here you have the perturbation interacting Hamiltonian. Here you have U naught. So one thing I can do is I can iterate this. I can iterate, and I'm gonna get, then if I iterate this, I end up with a series which has nested integrals, which is what we derived using a way that is much messier. I mean, I'm doing this right now because I want to show you how powerful time evolution operators are and how you can use these things if you know the right resources. So for instance, if you iterate with regard to U naught, so I can have U t t dash U naught t t dash minus I h bar t dash t U naught t, no, it's t t double dash h int t dash U naught t double dash t dash g t dash minus or plus minus I h bar square, and then you're going to have U naught, you have T dash T U naught T T double dash H int T double dash, and then you have here integral from T dash T double dash, and you have this bit, which is U naught T double dash T triple dash. It's getting big. Hang on. Yes, T triple dash. Here is integral T double dash. Trying to make space. Here, I'll put this here, okay? U naught T triple dash T dash G T triple dash. Get rid of this here. Plus, then you have, so what you see is this here, for instance, is what you would have first order perturbation theory. This would be second order perturbation theory. And this here is like if you want to do first or third order and so forth. So what you do is you get this expression and you iterate over and over this expression, and you iterate over and over and over and over again. So you could use it, for instance, if you have this Hamiltonian. If you have H is equal to P squared over 2M plus VR minus R E E T. Let me make this big because this is these are operators. Then you could say, for instance, that this is your H naught, and this is your interaction Hamiltonian, and then you get a series over E, E squared, etc., e to the power n or more. Actually, you see that it's going to be here, you get E squared and so on and so forth. Or you could say, get the same Hamiltonian, like what we use sometimes for strong fields, and you consider the potential is a perturbation. So you say this guy, but then you have to know how to treat purely time-dependent Hamiltonians also, assuming they are H naught. This is beyond the scope of this course, okay? But I could say that I bring these guys together. They are H naught, and this is H int. I can do, but here you have to be careful because this is H naught T, so this is beyond the scope of this course. But I'm only making this statement here because I want to point out that there are other ways of getting all these perturbative expressions. So this would be like, for instance, what you would have for first order. This would have second order, and so on and so forth. Okay, but this is, please bear in mind, this is beyond the scope of this course. And to compute transition amplitudes, what you do is you just consider, so transition amplitudes, you just consider that you have a final state phi m, and you propagate t dash phi k. And you have to know also, when you start to get these nested things, how you put closure relations together to take into consideration the intermediate states, which is also a bit tricky, but it is perfectly okay. Okay, so closure relations used to get the intermediate states, because you are going to have those once you have second order perturbation theory, third order, etc., etc., etc. So it is actually very powerful. This is unbelievably powerful. So I hope you liked this lecture. And what we're going to do next is to see a few standard applications of first order perturbation theory, which are widely used, and they are really important for you to know. So thank you so much and have a nice evening.